Bien, listo.
Buenísimo. Ok. Ahora tiene que mover.
No, rápido, sí, avísenme.
Perfecto.
¿Arrancamos? Bueno, gracias por venir. Un poco la idea de estas charlas con profesionales como Frank es que se acerquen todos informalmente a ver cómo se trabaja en el ámbito profesional de la exploración minera. Él se va a presentar a sí mismo los trabajos que está haciendo y cuál es su perfil, pero sí les quiero contar cómo nació esto. Nació parte de un viaje que compartí con SEG-SGA hace unos meses atrás y me comentó el trabajo que estaba haciendo Frank en Cerro Negro, en el macizo del Deseado, y un poco por eso le dije que estaría bueno que venga a darnos una charla. Así que él está camino a Cerro Negro, mañana creo. You are going tomorrow to Cerro Negro. Mañana sube a Cerro Negro, así que le dije, bueno, aprovechemos y nos vemos hoy si vienen para acá. Así que bueno, solo eso quería anticiparles, así que la informalidad de esta charla, para que se sientan cómodos y le pregunten de su profesión, de cómo trabaja como consultor, de cómo se formó, dónde se formó, etc. Así que bueno, eso.
Gracias. Lo siento, pero mi español no es bueno. So voy a hablar en inglés, pero si quieren preguntas en español, creo que es posible para mí de entender un poco. Soy de Francia y hablo francés y inglés, pero no español. So, sorry for that. But yeah, so I'm very happy to be here today, and I'll be presenting on Cerro Negro. And as Diego mentioned, it is very informal, so you can stop me anytime you want, ask questions, because I'm just here for you. So feel free to raise your hand, stop, ask questions if you want to. Okay? And Diego, do you want me to explain a little bit where I'm coming from? Yeah, so, I have been working in the industry for 20 years, approximately, and I study in France, and in France we don't have any mining industry, so I didn't learn anything about mineral deposit at school. Everything I know about them, I learned it after university. So I did a master thesis in Canada, and then a PhD. I worked in Tibet, looking at translithoceanic shear zones and trying to understand their age, the amount of displacement they accumulated, and the geodynamic of the area. And after that, I did a postdoctoral fellowship for 1 year in the University of Hong Kong, in China as well. And I kept working on Tibet over there. And then that's the time where I realized that academia may not be for me. So I tried to go in the industry. And so I started as a consultant based in France. And I did that for 6 years. And so I worked with mainly junior exploration companies on a small project. I was marketing myself as someone who knows how to map and who knows about structure. So that's usually how I approach companies. I tell them, this is what I know. If you need someone like me, I'm here. And that's how I end up working with them. And to find these jobs, maybe it's something that you may be interested about, is my strategy is I went to conferences. So every year I went to the PDAC in Canada, and this is where I found all my clients. So I walk in the booth with all the companies, introduce myself, tell them what I know, and ask if they need someone, and that's how I end up finding jobs. So I worked for companies looking for various metals, gold, gold, silver, copper, lead, zinc, uranium during these years, and it was great because I learned a lot. Small companies are good because they don't have a lot of staff, so they end up asking you a lot of things you are not qualified to do. And by doing the things you are not qualified to do, it forces you to learn, and at least try to do that. And so it's a good learning experience. And then after that, I got an offer from Newmont, who is my current employer. So that was in 2012. At the time, I was working with a Canadian company in the James Bay area, in the northern part of Canada, when I was called by Newmont. And they were looking for a project geologist to work in the Solomon Islands. So the Solomon Islands, you may not know where it is, but it's north of Australia, east of Papua New Guinea. And I say, yeah, sure. And then they hired me, and I went to Perth, which is where I was based, and worked fly-in, fly-out from Perth in the Solomon Islands. And then the gold price tanked, so no more Solomon Islands. And then they put me on they knew I had a PhD in structural geology, so they offered me to look at the structures of some of the mines the company had in Australia. And at the time, we had 3 mines. We had the Boddington mine that we still have today, the Tanami mines, which we still have today, and the John D, the mine of John D that was sold a few years ago. Actually, John D, yeah. I'm not going to go to John D, but anyway. So I worked on that for a year. And then after that, there was an offer to move to Nevada for a structural geology position inside the company. So a bit like a consultant, but internal to the company. And so I applied and I got the job. So then the company moved me to Nevada in a very small town called Elko. It's a tiny little town, just about mining. There is nothing else, just miners everywhere. And I spent 6 years there. And then I moved to, I was transferred to Denver, where the company has its headquarters. And now I'm doing the same job, but instead of so when I was in Nevada, I was doing structural geology, but just for North America. And when I moved to Denver, I was doing structural geology, but globally. So for any mine or project the company has around the globe, I can potentially be involved if they want me to. So that's, in a nutshell, my path for the mining industry so far. And right now, I'm working on 2 projects mainly. Cerro Negro is one of it, and I'm going to go there tomorrow morning. And the other one is another epithermal deposit called Brucejack, which is in British Columbia. And Brucejack has almost the same age as Cerro Negro. It's also Jurassic, which is rare for epithermal deposit. But Brucejack is a lot more complicated than Cerro Negro because it has been deformed a lot during the Cretaceous. And so at Cerro Negro, at Brucejack, you have many deposits superimposed on each other. You have a porphyry alteration. On top of it, you have an epithermal veins. And on top of that, you have orogenic veins, all in the same place. And initially, Brucejack was interpreted to be an orogenic deposit because people went underground and saw the beautiful textbook orogenic veins. So flat veins, steep veins, the flat veins being folded, and but all these veins are posterior and they have no gold. All the gold is in the epithermal veins over there. But it's a very complex deposit. Same age as Cerro Negro, but a lot more deformation since the Jurassic compared to Cerro Negro. So it's a long introduction. I think it's okay. If you have any questions, I can answer, but otherwise. So today I'm going to be presenting on Cerro Negro. And there is another talk which is about structural interpretation using geophysical data. And the talk I have is longer than the time I have. So when I give it to you, I'll skip a lot of slides. I hope it's okay. And again, it's informal. So I'm just guessing what you're going to be interested about. But if you think it's not relevant, you can tell me and we can skip or we can spend more time on certain topics. All good?
Yes.
Okay, so Cerro Negro. And yeah, the first thing I want to say is, so 2 years ago, Newmont decided that at Cerro Negro, we are going to do a lot of, let's say, scientific work. So to try to find another deposit within the property boundary that we have. So at Cerro Negro, Newmont, that's the size of the property we have. Okay, so it's about 25 kilometers by 20. So that's where we have permits in which we can explore. And the idea of the company, and we have one mine here, which is Cerro Negro mine. And we also have another set of mineral veins that are going to be developed in the near future, which are right here. Then you can see that we also have a lot of land in which we think we may find more. So Newmont decided we are going to do a lot of science to try to find more of these guys. So this is the historical Eureka vein, which is an epithermal vein, no sulfidation. And that's about the size of it, which is summarized here. So like this vein, which was making a lot of money, was 700 meters long, 5 meters thick, 250 meters in vertical extent, and with an average grade of 10 grams per ton. So for Newmont, this is what we are looking for. We don't want anything smaller. So it gives us already an idea on the type of scale we need to work at, because we are not interested by small, tiny veins. We want big ones. So it depends what the strategy we are going to implement to find it. And that's the Eureka vein on surface. So this vein was somewhere here. And so it crops out very well, but on surface, the grade is not very good. And, but at depth, that's how the sand vein looks like, and here the grade is this type of grade. So the goal game for us was to produce a structural interpretation, for me, to produce a structural interpretation of this block, and that's the final product that you see here, the final product until tomorrow. I go there and we start changing it. And I'm just going to walk you through how we build it. So like before I start on any project, I look at what's pre-existing in terms of work. And at Cerro Negro, in terms of structural interpretation, we had a few structural interpretations that were what we call linear enhanced type of mapping. So that's the two most recent ones that were made by external consultants. And so, if you look in the literature, what is the definition of a linear map, you're going to find this definition. So basically, linear maps, you take any type of geophysical product, satellite imagery, whatever product you can find, and the approach is just to look for lines in it. And you digitize these lines, and once you have done that, you're going to think about which lines could be faults, and you produce an interpretation with faults and main linear maps, something that looks like that. So the problem with this approach is that you end up, like at least for these two scenarios, the interpretation we end up getting are not feasible, they are not possible. When you look at it, you can see very quickly that the interpretation cannot be correct. And so some of the red flags you can see on this interpretation is, for example, you're going to have, let's see if I have another slide. No, I don't have another slide. You're going to have cross-cutting structures that are cross-cutting each other, but they don't produce any offset. So that's not possible. And when you have a fault, by definition, a fault offsets the rocks it cuts. So if you have two faults cross-cutting like that and there is no offset, this is not possible. And there are also a lot of faults, which is unlikely to be the case. They are all very straight, which is also very unlikely to be the case. Faults are not always straight, sometimes they turn. And there are a lot of things that are not possible on this interpretation. And it's due to the fact that when you map lineament, to translate a lineament into geology is not straightforward because you don't know what the lineament is to start with. Your lineament could be a stratigraphic bed, it could be topography, it could be an intrusive contact, it could be a road, it could be the edge of a forest, it could be many things. So when you start by drawing lines without thinking too much about what they are, and you postpone the interpretation of this line to the very end, you end up generally with an interpretation which is not possible, just like this one. So long story short, we had to start over from scratch. And so, if this approach doesn't work, what are the best practices to end up with a structural interpretation that makes sense? And here I'm just putting some key points, but like step number one to build a structural interpretation, because we want to identify faults, and faults we know that they offset things, we need to map the things that are offset by the faults, to recognize the fault. Usually when you have a fault, it does not crop out very well, because when you crush the rocks, if you have a gouge, for instance, a gouge is not going to make a nice outcrop. Your outcrop is going to be weathered, and usually your fault is going to be in a valley. And when you're in the field, you're not going to recognize the fault. So you recognize the fault because you have what we call primary fabrics, which are the fabrics that form in the rocks at the same time as the rocks. An example would be rock layering. So if you have volcanic rocks, you have lava flow, you have pyroclastic deposits, and all these deposits form layers. And you know that generally these layers are horizontal, flat. So that's your starting point. And when you have a fault cutting across, you're going to see these layers being offset. And that's how you recognize where the fault is. So step number one is you map your primary fabric. So at Cerro Negro, I have put a few examples of such primary fabric. So here we have a coherent lava flow, which is andesitic in composition, which is sitting on top of an autobreccia, which is the top of the previous andesitic lava flow that is not cropping out here. And at the top of this coherent lava flow, you would find another autobreccia. And of course, you can see very well what the layers are doing on this image. Another type of rocks we have at Cerro Negro are tufaceous deposits. So here is an example of tufaceous deposits which have been silicified. And the image is not great on the screen, but you're going to trust me that here you have a lot of small, tiny layers that you can really see very clearly. They are dipping that way. And you can follow them for long distances if you walk over them. Okay. So that's your primary fabric. And of course, when you have one layer which is continuous, you know that there is no way you can put a fault somewhere in between, because if there was a fault, your layers would be okay. And here's another example of the rocks we see at Cerro Negro. So we have the same type of tufaceous material, and you can see they form layers in the landscape. And then you have this body here, which is a rhyolitic dome. So that's an image cropping out when it was in bed, but it's a dome. Rhyolitic, so it's quite viscous. So it makes a topo high, and then your tough deposits are building against it. So the workflow is as follows. So we go to the field, we map the primary fabric. But you remember, like, the box is pretty big, 25 by 20 kilometers. So if you want to walk every single outcrop, you're going to be there for quite a while. So what we do, we try to help ourselves with some high-resolution imagery. As we speak, one of the best layers we have is this layer, which is it's coming from an airborne survey that was collecting hyperspectral data, so looking at different bandwidths of the rocks. The first goal was to identify alteration minerals. But the resolution of this product is very high. So like you have the size of the pixel is less than 1 meter. We have that across the property. And so we can use different composition of spectral bands and get a lot about the geology from that. So we collect information on the outcrop, and then we use that to extrapolate laterally. So like for instance, here is an example of some of the primary fabrics we see in this area. So you can see this greenish color unit on the image. We were able to identify some layers, and with this image we can continue, we can follow these layers, and you can see that this particular layer ends up stopping here and stopping here. So we know that in between this point and this point, there is no way we can put a fault, because there is no offset. So if we want to put a fault, we're going to have to put it beyond the extent of this line. And if you have enough primary fabric map, you can start getting an understanding of where your faults must be. Right? So that's, you move from that to that. So now your primary fabrics are the black lines, and the faults are red color. So that's step number 2 if you want. And then, of course, concurrently to that, you need also to pay attention about the stratigraphy, the local stratigraphy, especially in volcanic terrains. So you're going to look at, here I have a white color unit, then I have a green one, then I have another white one. So you start, and I can see which way they dip when I'm in the field. If I'm not in the field, I can use a 3D modeling software, rotate, so I can see the strike and dip of my layers. So here you can see some nice layers, and if you rotate appropriately, you can get a feel for how they dip. So knowing the dip of the layer, as well as, so you're going to know that the white one is underneath this one, and this one is above this one, because everything is dipping that way. So you start building a barcode. You start building a local stratigraphy in between each of your fault blocks. Okay. So you have many small stratigraphic columns, and then if you also collect information about the lithologies and the spectral signature, the geophysical signature, everything you can collect from the field, you can correlate across the fault which is which. So maybe this green unit is the same as this one, and maybe we had an apparent offset which would be right lateral in this case, and that's how this interpretation was built, right? So you can start making correlation across faults. So like you build your stratigraphy, at the same time you collect your structures and your primary fabric. So, and the reason why it's important to do that is because volcanic terrain, so that's an example from PNG of the sections across volcanic terrain, and you can see the scale. Again, like this is 25 kilometers, so we probably dealing with this type of heterogeneity. So if you were to use one single stratigraphic column here and try to apply this one single stratigraphic column across the board, you will have problems, right? Because a lot of your units may go very far. Okay, so this one may be the same age as this one, but totally different lithologies. So that's why you need to have, here we built a lot of small stratigraphic columns, and then through the workflow I'll explain on the previous slides, you can correlate which correspond to which in terms of age. Okay. So that's how you build your interpretation step by step. So it's just like a very big puzzle, and you constrain your puzzle step by step. So that's, these little images are showing the hyperspectral signature of these units, so to help people recognize them when they look at the satellite image, airborne image. And here is kind of a synthetic stratigraphic column, which is with all the correlations across it. And this is where the goal was in place in terms of age. So we have some geochronological constraint in this area, and so you can also use that constraint to put absolute ages on this relative stratigraphy.
Frank?
Yeah.
What are those pictures? Are rocks?
So these pictures, they are screen captures of this image. So just to highlight how they look like on this particular product. But so we have a bunch of, you can have the same for geophysics. So just to give an idea to the people who are reading the map, say, ah yeah, when I see this type of colors, I may be in this part of the stratigraphy. So it's just a work document. Yeah. So now what I'm going to do is, so through this process, you end up getting the timing, and you're also getting the timing of the fault, right? Because if your faults are cutting only this part of the stratigraphy, then your fault has to be younger than that, and older than that. So you can also get ages on your fault. Okay, and now in the next slide, I'm going to walk you through the geodynamic evolution we have tentatively established for this area. So we are going to start with the oldest structures, and we are going to move toward the youngest structures. And of course, it's an interpretation, right? So it may change. But I'm going to just show you what we have today. So like the oldest structures, again using the stratigraphy and cross-cutting relationships, are these structures that are trending northeast. And you can see that they are choked by younger structures that are red color on the map. And so these structures that are trending northeast, when we look at the stratigraphy, their age suggests that they would be slightly younger than gold time, or maybe they overlap with the beginning of gold emplacement time. Okay? But these structures are generally not mineralized. There is no grade along these structures, so that makes sense with that as well. And so, okay, we have some northeast trending structures. So if we, and that's their approximate age, this box. And then when we think, okay, what could trigger the formation of structures with this orientation at the time they form? So we know that this is Jurassic here, okay? So in the Jurassic, that's how the subduction was looking like. And we have the Deserto Massif right here in blue. Okay, so if you try to put these structures to where they were at this time, they would have an orientation approximately like that, relative to the trench. So they would be close to be at 90 degrees to the trench. Okay. And in the trench, you can have many things that happen, but you can have a strong coupling, which means that this plate which is subducting is going to be pushing into this one. And when you have this type of coupling here, you're going to have a lot of compressive structures, and the normal faults you may form are going to be at 90 degrees to your trench. So maybe this normal fault at 90 degrees to the trench form under this type of setting when we had a relatively strong coupling in the subduction zone. So that's a working hypothesis. And then right after the formation of these structures, now we also develop normal faults and strike slip faults. But the normal faults are almost at 90 degrees from the previous one. So like now, this is a zoom. This is a zoom into this part where we have a lot of gold. Okay, so we're going to zoom right in this part. So when you look at the mineralized veins, you have two main orientations. You have the green ones here that are along normal faults, dipping to the northeast or dipping to the southwest. We have both orientations. And we also have some more east-west faults that are subvertical, and sorry, the ones that are normal, they dip between 60 and 90 degrees, which makes sense with normal faulting because in epithermal system, normal faults, they become vertical close to surface, and they dip 60 degrees when you are deep enough. So here we are seeing different elevation in the paleo topography. So it's why you get these structures dipping between 60 and 90 degrees. Whereas this one, which are east-west, they are almost always vertical. And here is an example of one of them, for Marcos. Okay, so we have two familiar faults, and these ones, they have, according to underground mapping, a dextrose component of speed. So, which works with subvertical faults. Right? Strike slip fault usually has subvertical. So, okay, so we have a mixture of normal and strike slip fault. Two types of orientation, north 300 for the normal fault, and north 85 for the strike slip fault. So now we need to know, are these faults newly formed, or are they pre-existing faults that get reactivated? So to address this question, we can look at what people have done in the region. So people have been looking for oil in the region, so they have some seismic lines, and they have some field data in many places. And that's a compilation of the deformation history prior to the mineralized fault we have just talked about. And you can see that prior to this normal and strike slip fault, the faults that have been documented have a different orientation. There is no east-west fault in any of these older events, and there is no north 300 fault either in this older event. So it suggests that these faults were newly formed. They formed from scratch. They did not exist before. So that's an hypothesis we're going to live with. And then the next question we need to ask ourselves is the east-west and the, let's call them northwest fault. Do they form at the same time? Or do we have one of these two being slightly older or slightly younger? So you're going to look at cross-cutting relationship. And here it is just mineralized veins that are dispersed beside. And when you look at cross-cutting relationship, you don't see neither one or the other cross-cutting and offsetting the other. It seems that they join together, but they don't offset each other. So it suggests that they form a fault system. So faults with different orientation, but were working at the same time, or more or less at the same time. There is no, like, you don't see this one offsetting this one, and you don't see this one offsetting this one. They just connect, but don't offset each other. So, because they are newly formed, and they form roughly at the same time, we can try to do a paleostress analysis and see, okay, how could we possibly make these two faults with different kinematics and different orientation at the same time? So in one case, so the normal faults, if you interpret that in terms of paleostress, this is what you would get. So to form a normal fault with this orientation, you would need your vertical principal stress to be sigma 1, and your horizontal paleostress to be sigma 2 and sigma 3 with this orientation. And to form your strike slip dexpole fault, this is what you would need in terms of paleostress. And you can see that they are quite similar in orientation. Like this one is parallel to this one, and this one is parallel to this one. But the difference is that the vertical one here is sigma 2, whereas here the vertical one is sigma 1. So how can you possibly switch from that to that very rapidly during gold time, knowing that gold time only occur in a tiny window of 1–2 million years max from the geochronology we have. So a working hypothesis to explain that is displayed on this slide. So as we are dealing with, these structures are mineralized, right? They have low sulfidation epithermal veins. So from what we know about these systems, they need the fluid that mineralize this vein needs to come from a magma at depth. And typically the depth would be 4–5 kilometers. That's what we have on this axis. So we probably have a magmatic chamber somewhere below this fault. And you know, like any magma chamber, sometimes you get a magma recharge, and sometimes you have periods where the magma is cooling and there is no more magma coming in. So when you have a magma recharge, the magma being hot and light compared to the host rock, the magma is going to exert a vertical stress which is going to go opposite way to the gravity. So it's going to decrease the magnitude of this guy. And then when your magma is cooling down, gravity stays gravity. But you have no more pushing upward from you. So now you end up with sigma 1 being vertical. So if you have this mechanism going on during mineralization, which we know we do because you need a magma to form these deposits, you can alternatively activate the normal faults and mineralize them, and then activate the spicy fault and mineralize them, and you can go back and forth multiple times through 1 million years or less than 1 million years.
So, Frank, there's two groups of faults. They were produced just in the Jurassic. They were not pre-mineral faults.
Yeah, yeah, and that is we know that from the original work. So it's a working hypothesis, but there is no evidence for such faults to be pre-existing. But maybe there are evidences, just I'm not aware of them.
Well, if you go to, for example, to Cerro Negro, you will see that most of the veins are not closer to the east-west, they are normally in the northwest direction.
Okay.
So there must be something there in the western side of the massif that creates these east-west structures. Yeah. Interesting. And among the textures, do you find differences between the two strikes and the textures? Because one is more strike-slip and the other one is more normal.
Yeah, not really. I don't really see. And you know, like if this mechanism is correct, you could argue that where you don't have these guys, because you know, like to get this mechanism work, you need to have the right differential stress, and you need to have the right magma push. So if you have a slightly less magma push, you may not form these guys at all. If you're not pushing hard enough, it could still be sigma 1 here, and then you're only going to form these guys, and these guys will not exist. So I think you don't, yeah, so.
No, I like this idea. We have this in between, you remember? But Minamata is exactly the same, but in Wino we have two different directions. They are almost orthogonal, they cross cut 90 degrees.
And they are both mineralized.
Yeah, more or less at the same time, but we have this dome here.
Yeah.
Really clear. So it looks like the dome is much closer to the surface, so
yeah.
it was really clear. So that probably created two structures more or less at the same time.
Yeah.
It's interesting.
And if there are 90 degrees, you would probably need a very low differential stress, because to switch 90 degrees, you need to, you know, like you need to realign.
And they don't cross cut. I mean, you have two mineralized.
Yeah. So they were formed almost at the same time.
Yeah.
Frank, question. Gold mineralization prefers one type of fault over the other, or it doesn't matter?
I mean, is there one of the two being slightly younger?
No, if the gold mineralization is, if one or the other favors more mineralization than
okay, yes. This one have, let's say, 75% of the money will come from these guys, and these guys the remaining. So these ones are really the money maker, are these ones. And you know, like now, if we go back to the regional stress, here we will need a different tectonic setting compared to the northeast structures. But like, you still have the same substitution active because you're only a couple of million years younger compared to the northeast structures. But like this time, to form faults that are parallel to a trench, instead of being perpendicular, you would need to have some slab tool in the subduction zone. So maybe there was a rollback, or maybe in the previous event you had an oceanic island getting into a subduction or whatever. But that's kind of what you would need at the boundary of the system to form faults with this orientation. So this time they would be parallel to the trench. So maybe the gold happened when we transitioned from a period of slide push into slide pull. And as soon as we do slide pull, epithermal mineralization. That's what it seems to be. And then posterior to mineralization, so posterior to emplacement of the epithermal precipitation, epithermal vein, we have a little bit of deformation. And so this is a map from underground. So we are at the level 390. So that's underground mapping, as well as supported by a lot of drilling. So like the geometry on this level maps is very well constrained. You have a lot of drilling, and these veins have been mined. So we know exactly their geometry. There is a very little uncertainty. And you can see that the veins are not perfectly flat, they are undulating. And so these veins get folded after emplacement, but very gentle folding, broad open fold, meter scale amplitude. So that would be the actual veins. And so to form a fold with this geometry, the folds are symmetrical. You will need to squeeze horizontally in an approximately east-west orientation, because these veins are north is that way and north is that way. So that's the strike slip dextral veins, that's the normal veins. So you need to get a horizontal east-west compressive event and very low strain. And for the normal folds, same story, they also get strain, but because of their different orientation, instead of developing symmetrical folds, they end up developing asymmetrical folds when you squeeze them east-west. So it's quite nice. And so at the regional scale, when you zoom out, you don't see the folding because it's meter scale. But when you are mining, the folding, so at the regional scale, we don't care about that because it's very low strain, so we don't see it when we zoom out. But when you are mining, it's very important because it's causing a lot of trouble in the mine because they have a plan to mine this thing, and usually their plan looks like a straight line. And then when they start mining, on the face they see the vein, and the next day, oh, the vein is there, and if they keep going that way, they're going to miss it. So they have to adjust, and they have to turn, change the plan, go that way, and then the vein move back, then they have to change. So every day they have to change the plan. And it's a real headache for them. It's very difficult.
So, Frank, what kind of deformation is that? Is subtle or is it kind of fragile?
So, like
because it's really shallow.
Yeah. So the veins are folded, and so the type of the deformation style you're going to see depends on the rheological contrast between the objective fold and the host rock. So here we have quartz vein. And we have andesites in this case. So when you have this type of rheological contrast, you end up folding these guys quite nicely, as you see here. And when you look at the tectonic evolution of the area, there is a compressive event in the Cretaceous and another one in the Miocene. Yeah. The Miocene one being the biggest. So maybe this deformation is Miocene in age, maybe it's Cretaceous in age. But in this area, the strain is super tiny. Because another thing I'm not presenting here, but I could present, is that we are not forming any newly frost. There is no frost associated with this event. So it means that the strain was not high enough to develop new frost folds. And if we were developing new frost folds, they would be north-south, they would be tilting 30 degrees, one way or the other, and we don't see that anywhere on the property. We see some faults like that, very rare. There are a couple of faults like that get reactivated in reverse, but only a couple of them. And the reverse displacement is quite small. So yeah, very low strain event. And then I'm just going to say something about exploration targeting. So now that we have structural interpretation, and I have explained how you build it, you get a story, a geodynamic evolution that makes sense with the original setting. So you know that your story is possible. Doesn't mean it's true, but it's possible, and that's important because a lot of the stories are just not possible. And yeah, so now that we have that, how do we utilize that to find new deposits? So from this mapping, we know the folds that were active during gold time, and we know that the normal folds are the most prospective one. but we still end up with a very big area to explore, if we just say that, because if your fault is 10 kilometers long, you're not going to be drilling for 10 kilometers along it, right? It's too big. So you need to go beyond that. So one approach you could follow, if you just want to utilize structures and squeeze as much as you can from the structures in terms of targeting, you can use the concept of slip tendency and dilation tendency. So like from the mapping, we have an idea of the geometry of the faults. We can see where they turn, we can see the strike they have, and we have an idea about their dip, because they are normal faults. And from this geometry, you can calculate how likely a fault segment will dilate or will slip. Okay? And so you can, and of course, where you get your maximum dilation on this diagram, this is here, this is where you end up having your deposit or your best mineralization. So where the dilation is maximal, this is where you have a higher chance to have something economic. So you can use this working hypothesis to do something like that. So I'm going to go fast on that because we otherwise are going to be here forever. But like what we do, so you remember, we probably had switched back during gold time between normal faulting, strike faulting, and it goes back and forth. So we are just going to talk about this situation, but like in this situation, based on the orientation of the faults having this edge, and these are the faults having this edge on this image, you can calculate their dilation tendency. And red color means very high dilation tendency, and blue color means very low dilation tendency. So now if you take one single fault, let's take this one, you can see that this fault is very low. But if you look at what areas are red color, now you have a very small section of fault to look at compared to your initial fault length, which was very long. So you can decrease your search space a bit more using this type of approach. So like, and you can build your own recipe, but like in a nutshell, this is what we did for this particular exercise. So you know, at Cerro Negro, if you put that in a block diagram like this one, so you have your normal fault, north triangle, you have your strike slip fault, north 85, and this one makes 75% of the money. So when we are in the hanging wall of such a normal fault, having the perfect orientation to be highly dilational, we are going to put a score of 3. And when we are along a fault like that, which represents only 25% of the gold, again having the maximum, the perfect orientation to have the maximum dilatancy, we are going to assign a score of 1. So this is because 75% of the money, 25% of the money. And so when you have intersections, this is where you're going to get the highest possible score, being 4. And then when the orientation of these faults change, this score is going to decrease as the dilation tendency decreases. So this is just the maximum score you can get. Okay? And these intersections happen to be the best mineralized zones on the property. So we think that this technique of scoring the fault is appropriate for this deposit. And then you can do that automatically. You can do this calculation automatically using ArcGIS Pro. So here, I don't know if you're familiar with ArcGIS Pro or ArcGIS, if you have been using that, but in this, in this GIS platform, you can do a lot of cool stuff. So like for instance, here you can take your fault mapping, which is the blue circle, and then you can split your fault, let's say, by segment of 50 meters, 25 meters, whatever is appropriate. And then from there, you can do some calculations. So the calculations you see on this screen are the ones that are summarized on this one. Right? So at the end, you can get a structural favorability score, if you want, which is that. And the score goes between 0 and 4, which is what we have here. So you can get maximum of 3 along this guy, maximum of 1 along this guy, and maximum of 4 when you have an intersection between the two. So that's how you end up with a map like that. And then, from a structural standpoint, the red zones are the ones that looks the best. And then the next steps, of course, is you don't use just structures. You need to use other layers. So, like geochemistry, alteration, and and geophysics. So all these other layers, and geochemistry from the sinters, geochemistry from the soil, all of that. So you need to use all the other layers to get to a geological favorability score at the end. And that's what we are going to be doing next week when I go to Cerro Negro. And I think that's it. Yeah, so I have been talking for quite a while, but is it okay if I show an example?
Yeah.
Okay, so like some exploration implication know that we have said that. So let me see. What do I have here? Yeah. So like the idea is that if I go back on the previous slide, so the next slide I'm going to show you is an example of, so once you have your geological favorability score, the red colors are the best zones. So then, before you do the drill rig, you need to zoom in and have a closer look to make sure that what you have highlighted as being highly prospective is making sense. So as an example, I'm going to show you this anomaly that we have here, which is a nice red color one. And so when you zoom, that's how it looks like, the structural interpretation. So you can see like this red color fault would be the feeder structure, and it's dipping to the northeast. There is another one that connects to it, which is more east-west, but also probably dipping to the northeast. Okay? And then when you look at the gold assays and the arsenic assays we have in the soil, you can see that the mineralization, or at least the arsenic and gold, is in the hanging wall of this fault, which is what you expect, because if you have a normal fault like that, your alteration is going to be mainly in the hanging wall. So far it's making sense, right? Also, another thing we can see is that the blue unit, which is an igneous bright, is not offset much. So that's an igneous bright, that's a picture of it. So again, that makes some sense, because the higher up you go along this fault, the lower the offset is, right? Because this fault they move at the same time stratigraphy is deposited. So, so when you look at arsenic, gold, silver, antimony, mercury, we can see some zoning from top to bottom. So you have mercury at the top, antimony underneath, arsenic underneath, gold, silver, and then gold, okay, and then base metal. And here we see the same thing. So like when you look at the arsenic, you have a big cloud. When you look at the gold, it seems that your gold is a little bit deeper in the stratigraphy. You have more gold in the peak and less gold in the blue. The pink is below the blue, stratigraphically. You have a bending measurement here. Stratigraphy is quite flat. Right? So it's making sense with this zoning. So on surface, you are probably in this box when you look at the metal zoning that you see. And then we also find a small outcrop of small sinter outcrop, just one. So again, like like your sinters are going to be somewhere here on your section. So for all these reasons, we think that on surface we are probably looking at the upper part of a potential epidermal deposit at depth. So then, to drill this target, we will need to drill somewhere here to find what's going to be making money, right? Because you need to drill where you have your boiling zone, right? So that's how we set up the drill target here. So we put the drill rig here and drill that way to try to hit that zone. And if you go back to the first image we had about the previous structural interpretation, which was linear based mapping. So all these these red color measurements are small, tiny veins with a lot of gold that were measured on surface, but like centimeter veins. So none of that is economic. You can see that they are mainly in the hanging wall, but like when you have this structural link there, you have no idea where to go. If you were to drill based on that, where would you go? So what people did, because that's what they had, is they did what I call an octopus type of drilling. So they go where you have the highest grade, and they drill that way, that way, that way, and hope for the best. And that's because they do that, they probably drill, you know, somewhere in the hanging wall in multiple directions, and then they end up finding the same thing as on survey. So that's the drilling they did. So that's the drilling they did, like octopus type of drilling. And they never get across this route. So then they end up walking away from the target. And then after doing this work, we are coming back to this target because now we know what the target is, that's this normal fault, and we know at what depth we need to go. So I guess that's the idea. That makes sense. Yeah.
You drill that?
Yes. Sorry?
You drill that?
Yes, we drill it, and we end up finding veins, but not economic. So here we think that, and the size of the anomaly here is quite big. I haven't put the scale, I have a scale. You can see like it's 1.5 kilometers. So, but the rocks are ignimbrite, so we think that maybe ignimbrite, the fluids were able to disperse. They were not focused enough. Yeah, like we didn't have one nice crack with nice fat vein. Instead, we had a lot of small tiny veins in a big cloud of ignimbrite. So that's no way to. But actually, that's on this guy that we ended up finding the best looking vein, but still it was not making the cut in terms of economics. So anyway, that's it. Any questions?
If you only have those tiny veins and you can't find any of the fat ones, what do you do? Is the grade high enough to try to mine that, or?
For Newmont, no, because so for Newmont, so again, it depends the company you are working for. So depending on the company you're working for, you have a target in size, in your head. So for Newmont, it's a Eureka West type of vein, so you know it needs to be 10 grams per ton, 5 meters thick, 700 meters long, and 200 meters high. So if you look here, this is 1.5 kilometers. So if we put 3 drill holes at the right depth and we hit nothing, we know it's not going to be a Newmont size target. Maybe there is a target, but for the company I'm working with, it would be too small. So that's how we can decide where to stop. That makes sense.
Yes.
So yeah. And maybe if we keep working and we come with new ideas and change the interpretation, maybe we are going to realize that there is a flaw in this interpretation. Maybe the interpretation is wrong, and maybe we should be looking elsewhere. But as we speak today, that's what we have in our head. So you need to come with a target concept, and then you set up a drill plan to test this concept. And then once you get your drilling, you get your answer. You know, maybe you find the fault, but you don't find the gold. So it's a technical success, but no good for your company. Or you drill and there is no fault. So it means your interpretation is wrong, and you need to rethink, change it before you drill the next hole.
You did this level of detail in every analysis, in every sector with utilization on the faults on the area, because I think it's like really great to like take out the noise of the previous things and you did it in every, because it's a
It's a big area, so it took a lot of time.
but it is worth it.
Yes, we think. Yeah, now we are at a stage where this is structural interpretation phase 1, but now, as I was talking with Diego, we are getting a lot of new data sets. So gravity data, ground magnetics, resistivity data. So and geochemistry, we sample the entire property with soil, tons, many samples, like thousands of samples. And so we are going to analyze all of that and see if the interpretation needs to change. And so we are going to try to produce our best possible interpretation with all the data we have. And based on that, define targets and test them.
And other cases similar to this one have been economic?
So far, no, because so far we have only tested this one.
Okay.
But we need to finish the work so that during this year they are going to test other targets. So that's where we are at. Yeah. Yes, that would be good.
Frank, I have a question. How is that like the relationship between all this structural setting and the center, for example, that I'm looking now?
Yeah.
Like, is there any relationship, like, for example, this main structure is working like a feeder for that center or something like that?
So that's that's a very good question. And in this specific area, we don't know because we only have one center out of that scene, so it's not very clear.
Okay.
And but like there are other areas where Diego worked in the past, where we have identified multiple levels of silicification. Maybe some of them are just water table silicification, others are real sinters, and we have been assaying them, and I don't know the results yet. But as we have multiple sinter levels, there is maybe only one that is associated with mineralization. Maybe there are two, maybe I don't know. So depending on the geochemistry we are going to get in these sinters, maybe we get a better idea. Maybe some sinters are going to have some mercury in them, and others will have nothing. I don't know yet, but that's why we are also doing some geochemistry on top of the stratigraphy and everything else to try to get a better idea on the relationship or potential relationships between some of the sinters and economic veins. Because where we are mining now, the sinters are no longer here. They have been eroded away. But we are all other places in the property where we have sinters, but we haven't found any economic mineralization underneath them. So the idea is...
Yeah, right. I think that it could be like a very good evidence to prove your idea, your theory.
Yes.
If the setting is like that,
yeah.
you can go and look for that in the sinter if you have like some evidence of that, and you can follow.
Yeah. No, definitely. Yeah, so more work to be done.
Thank you.
Yeah, thank you. All good? You want a break? Or you don't want a break?
We're going to switch to the other topic.
Yeah. Unless there are...
Maybe if someone has something else. ¿Alguno tiene otra pregunta? De esta forma
Sí, nos tomamos un recreito. 10 minutitos.
So we're going to have a break.
Okay. Yeah, the next one I'll keep it short. I'll just keep some highlight because I didn't talk too much. So,
Because of the hosting there in Cerro Negro, we are not find
Saco la factura.
yeah. I know, like, now
Yo le quiero hacer más. Bueno, no tiene ningún pausa. No, última hora. Sí, ¿no?
Cerro Negro, technique.
Vamos. Listo. So we will keep it very short, 20 minutes.
Sí. Yes.
Yeah. So this is a very broad topic. We can spend a lot of days presenting on that. Actually, just before coming here 2 weeks ago, I gave a short course, 2 days short course on this topic. So like to do it in 20 minutes, it's quite a challenge. But I'm just gonna give you a few little things, and yeah, that's it. So let's jump. So you know, like this figure is really basic. We don't need to read what's on it, but it's a summary of the main step of the workflow that I follow to interpret geophysical data, and actually to interpret also satellite imagery data for structures. So there is a strategy piece. I'm going to talk about it very quickly. But basically, the strategy is quite interesting. Yeah, we'll talk about it. And then geological review, data preparation, and then you have all the steps to do your interpretation. And once you have your interpretation, you move into targeting, and then you end up drilling your target. So like for the Cerro Negro example, I show you that. I show you some of that. And I show you a little bit of that. Okay, but like, so maybe for this presentation, yeah, we'll see how far we go. Okay, so strategy. So the example I was planning to use in this presentation is a project we had in Ghana. So Ghana, that's how it looks like on surface, this area. So you know, like when you are close to the equator, you get tropical forests, you have very little outcrop. With the rain you get, when you get outcrops, they look like that. So you cannot really see much geology. So you cannot build a structural interpretation from few scarce exposures like that. You need some help from other techniques to see through the regolith, which is the weathered part of the surface. And so this is when we use geophysics quite a bit. And you do have some good exposures, but that's how they look like. And of course, when you are an exploration company, you don't have something like that to look at the rocks. So people, for instance, they use a lot of core structural measurements. So that's an example of a team in Ghana collecting structural measurements from core. So that is a broad topic as well. There is a lot to say about the techniques you can use to do that. But we're not going to talk about that today. So like, in this particular example, the box, the land tenement we have is gigantic. It's 4,000 square kilometers. So 100 by 400 kilometers in size, and that's all the geophysics we have in this area. So, you know, like in a lot of the literature, we are going to read about magnetics, because magnetics is a very popular technique, and there are a lot of free magnetic data that are available. So a lot of people from the universities, they try to teach geophysical interpretation using magnetics for this reason, because you have 3 data sets. But in the mining industry, we use a lot of other techniques. And here is a good example. So we have gradient array, which we measure the resistivity and the chargeability of the rocks. Of course, we have magnetics, and we have different resolution. We have high resolution magnetics, low resolution magnetics, and we also have some gravity. And AGG is airborne gradiometry gravity. So we have a variety of techniques, and we need to find a way to integrate the findings we get from these techniques into one interpretation that can help us to find the deposit. So maybe the first thing we need to ask ourselves before we start jumping into the interpretation is what type of deposit are we going to be looking for? Because different deposit types have different structural controls. For example, epithermal deposit, like Cerro Negro, we don't really care about the folding, right? Because epithermal deposits usually folding does not control the mineralization too much, right? For orogenic deposits, which is the case in Ghana, it's a different story. Orogenic deposits are tightly controlled by folds. So if you know the type of deposit you are looking for, you're going to adapt your interpretation to that. So in Ghana, this slide is just showing you that most of the mineralization we are dealing with are orogenic. So we are going to be looking for orogenic deposits. And so we look at the literature, and we try to make a short list of the structural controls that control this type of deposits. And if you do this exercise, you would get something like that. So you have a first order translithospheric or transcontinental structures that are connected to antiforms. So mineralization are in red color on this diagram. So like you can see that all the mineralizations are in the antiforms. They are not on the synforms, even if there are exceptions to the rule. And you get second order structures or third order structures. You get contact between sediments and volcanics. Rheological contrast are intrusive. You also get rheological contrast in the stratigraphy, so like the peak unit is more competent and contains more iron. So, long story short, you figure out all the controls that you hope to interpret so that you can find one of these deposits. Okay. So once you have an idea about these controls, the next steps to me is you need to manage expectation. So usually you work for a big company like me, or you are a consultant and you work for any company, and they are asking you to do an interpretation of the area. And you need to give them an idea, and they give you a timeline. They tell you, okay, you have 2 weeks, or you have 1 month, or you have 2 months, or whatever. And then you need to tell them what they are going to get within this time frame, so that at the end there is no disappointment. And also, when you work for a big company like me, sometimes they don't know the time frame. They ask you, what do you think is a reasonable time frame to do this work? So same story, you need to tell them, if I spend that amount of time, you're going to get that. If I spend that amount of time, you're going to get this. Right? So they can make a decision that's appropriate. So how do we do that? So like it's a cost-benefit analysis. So the cost is the time it's gonna take you to interpret the data, and the benefit is by how much you're gonna reduce the exploration search space. So we start on this project with 4,000 square kilometers, and by doing this interpretation at the 150,000 scale, at the 100,000 scale, at the 120,000 scale, or at the 5,000 scale, we are going to reduce the search space by X, Y, Z. Okay? So that's the general idea about that. So I'm going very fast, but please stop me if I go too fast. So in the literature as well, you know the size of all these controls. You have an idea about their size. And from the literature as well, you like looking at for orogenic, you're going to look at what's going on in Bolivia, in Australia, what's going on in the Abitibi, in Canada. So you're going to look at all the big districts that have been very well explored for orogenic. And from there, you're going to get an idea for what is the typical distance between the structural controls and the deposits that are economic for my company. So for instance, the first order transcontinental structures, typically most of the deposits are within 7 kilometers of them. So if you put yourself within 7 kilometers from one of these structures, this is where you're going to find 90% of your economic deposits. So you can do that for each of the controls, right? So you have an idea on how far the deposits are going to be from these different controls. And then you can say, okay, if I was interpreting the area at this scale versus this scale versus this scale, so you put a number of scales here that are reasonable. And then you're going to say, okay, at these different scales, which of these features can I possibly identify confidently? So like a first order channel, a first order structure, which is transitospheric, it has a strike length which is greater than 10 kilometers. We know that structures that have a strike length of 10 kilometers, they are going to have offsets that are going to be greater than, a few hundred meters. And now, if you interpret at this scale, you need to be able to see the offset this structure is going to produce. So you can look at this scale, yes or no, can I map a structure like that? And for this one it's yes. And then for the second order structure, at this scale you would only map few of them. The third order structures, you would have zero chance to map any of them, because you would not see them, they would be like joints, they would be too small. And you do that for each of the controls and each of the scale. And once you have populated a table like that, you can get, and you combine this information, you can get an idea about the size of the targets you're going to generate with an interpretation at this scale. So like if we were to do the interpretation at this scale, the size of one exploration target would be between 50 square kilometers and 700 square kilometers. So if your client wants to put a drill rig, and you are giving him that, he's not going to be very happy. Because then, okay, you can drill anywhere within this 50 by 10 kilometer box. And say, okay, it's super useful. Right? So that's why that's the benefit. So, and of course, the smaller the scale, the smaller the size of the targets and the beam. So here you would have a target size between 1 and 10 square kilometers. So here you are getting to the point where you can possibly design a drill program from that. So you need to be clear from the get-go with your stakeholder what he or she will get from the work you're going to be doing. So if they give you 2 weeks to do the work, then the best I can do in 2 weeks is that. Are you going to be happy with that? And the answer is going to be no, because this is useless for me. And then you don't waste your time doing something they are not going to be happy with. But in my experience, if you don't do that, you are going to put yourself in trouble at the end. Most likely. So I always start with that. And then how much is it going to cost me to do the work at this scale, this scale, this scale, this scale, or this scale? How much time do I need to do that? So you can do a quick assessment. So you can say, okay, these are all the layers I have. So I have carbon magnetic with this spatial resolution. I have radiometric, radiometric, so I have all these layers. And I can say, okay, if I was interpreting them at the maximum, at full resolution, so maximum resolution, you can calculate, how many letter size map you would need to produce to cover the entire area at the different scale. And you can say, okay, if I spend 3 hours per map, how many hours do I need to interpret the entire area at a given scale. Right? And 3 hours is not a lot to integrate all of that per A4 paper size. So when you do this type of exercise, you can get an estimate of how much time you're going to need. So for instance, if we were to interpret the 4,000 square kilometers at a 120,000 scale, it would take 500 hours of work if we were to spend only 3 hours per map that big. So 500 hours of work, that's a lot of work. So, and you have to do that for all the layers. So at the end, you're going to be with thousands, like you're going to be spending a PhD to do the okay? So you can get an idea about the cost that way. And then once you have your cost and your benefit, you can set up a strategy. So for Ghana, because the area is so gigantic, we cannot interpret everything at this scale, because it would take forever. So we decided to do, okay, we are going to do a very regional scale interpretation, 150,000 scale. It's going to be phase 1, 150,000 scale, and it's going to take us 300 hours, which is still a lot of time. And with that, we are going to get targets that are going to be 10 to 40 square kilometers. So we cannot drill with that, but it gives a general idea. And then, within these targets, where we do have geochemical anomalies, we will do smaller interpretation, smaller size interpretation, at the 1,500 scale, and then we will use that to set up the drill program. So 2 phases. One phase, the entire area at a very coarse scale, and then second phase with small ones, just on where we have nice geochemical anomalies within these targets coming from the first one. So every project is different, but you need to think about that early on, because otherwise it's not going to work. Okay, and then once you have that, and you make it clear with the customer, so you get to a decision on what to do, you move into a geological review. And this part is quite important, because one thing about geophysics is for one geophysical response, you can get an infinite number of geological interpretation. So for this, for instance, for this magnetic image, you can come along with many different geological models that are going to satisfy the data. So to reduce, to get closer to the truth, you need to be cognizant of the deformation history of your area, as well as the different structures that are formed through this history. And this comes from regional work, from people in the universities, from consultants, from everything you know about your area in terms of geology. So for instance, in Ghana, you can see that most of the faults are trending northeast. Right? So if you start interpreting faults like that, you're going to be in conflict with what people have observed. Okay? So the idea is that you need to bias your interpretation to what you know about the regional geology. Because with that, you can produce an infinite number of images, and of course, 95% of them are going to be craziness. So like you can come with something like that. Okay, I have some breaks, I'm going to put some lineaments, and they're going to crisscross each other, and you know, something that doesn't make sense, so you can do that. But like, if you take into account the geological history of the same area, so here we know that we have one folding event, which is producing fold with this orientation, and then we get a second folding event, which produces fold with this orientation. And from these two orientations, you know that the type of folding pattern you're going to get is going to look like that in 3D. Okay. Because we know the orientation of these guys. They have been measured in the 3D. So you know that the type of pattern, so if the red layer was magnetic, your magnetic image would look like the red layer on this block diagram. And so if you compare with that, you can possibly say, okay, that's my phase 2 fold, and that's my phase 3 fold, and you are reproducing this, but you are seeing the geometry that you see in the red. Okay, so you can, these green polygons are the magnetic bodies. I forgot to say that. Okay. So now that you have that in your head, you can look for this pattern on your image, and you can come with a totally different interpretation, not on the previous slides, which was just knowing nothing, doing some crisscrossing faults. So you would say, okay, I have my two folding events, my 1 and my 2, and the 1 is refolded. So you get the same geometry as I have here. And then these folds end up being cut by a fold here. And now, you can connect the dots with that. And you can say, okay, maybe this is my first order structure. And now I need to look for these spots on this image to find my target. And they would correspond to these zones on the image, if the internet is correct. So that's kind of the workflow. Okay, so you need, because you know you're looking for orogenic deposits, you know that these controls are going to be important, so they need to be displayed on your interpretation, and you need to be cognizant of the orientation of the structures you have in your area, so you can recognize them in your geophysical products, and you can come with an interpretation that may not be correct, but that is plausible with the geodynamic evolution of the area. Okay, it's almost done. So I'm gonna go 5 minutes and then we stop. But that's the general idea, right? So then for the data preparation, I'm gonna go super fast on that. But so a lot of the targets, a lot of the deposits, they are no longer cropping out on surface. They have already been found, the one that crops out. So like for people of your generation, there is a good chance that you're going to be using geophysics more and more to find the deposits that are not cropping out anymore. So you need to familiarize yourself with all these techniques, because if you don't know what they mean and what they tell you about the geology, you're going to produce interpretations that are going to be not ideal, and you're going to miss opportunities. So, and geophysicists, they need to do the same. They need to learn about geology, so everybody can help each other. So this is a very good book to learn about geophysics, so you can read about it. And this one, there is not much mathematics. It's very much for geologists. So if you read this book, you'll get a very good foundation about the different geophysical techniques, and then you can use them appropriately. So I don't have time to go through all these guys, but they are all measuring different physical properties, and these physical properties correspond to certain geology. Okay, and yeah, the idea is that you need to connect the dots so you can get to an interpretation that makes sense. So we don't have time to go through all of that, so I'm gonna skip. But like the magnetics, they are, yeah, it's a bit complicated because it's bipolar, so you need to do some treatments to interpret magnetics properly. And yeah, so we're gonna skip all of that. Yeah, maybe just a few words about data preparation. So sometimes when you work for junior company or even major company, you are given a geophysical product, and as a geologist, because you are not an expert, you're going to have the tendency to trust the person who is giving you the product. So you have to be careful, because there are some data treatment that is involved in between the data collection and the image you are given. So this is an example of the same area in Ghana. Two different geophysical treatments of the same data. Okay. And you can see there is a huge difference. So both are magnetic image. So here you can see some magnetic bodies that are kind of east-west. And on this image, you no longer see them. They are all gone. And the reason why this is because magnetic data are acquired along the line the plane is flying along. And in between line, there is no data. So the geophysicists need to project the data collected on the line in between the lines. And when you do that, you can push very far away from the line or not very far away from the line. So like in this case, they push very far away from the line in that direction. And here, they didn't push too far in that direction. So here you end up with an image which is more representative of geology, whereas this one has been totally, you are overriding anything that is not northeast. And the reason why they push in this direction is because geologically, most of the structures are trending northeast in this area. So again, you need to be cognizant enough so that when you get an image like that, you can talk with your geophysicist and make sure that you get the right product. Because if you build an interpretation on that, you're going to have a very different story than building it using that. And this is true for all the methods. Okay. And then there is a ArcGIS type of setup, and that's it. So I'm just going to go, maybe I just show this one, and then we stop. But like, in a nutshell, when you are ready to go to interpret your data, I think I'm going to stop because I'm going to be talking for quite a while. I guess you got the idea. After that, the interpretation process is pretty much the same as for Cerro Negro. So, except that here, you are dealing with geophysics data. So, like for instance, okay, I'm going to go through that and then we stop. Okay, so, here, if you want to look at magnetics, and you have buildings, and the buildings have a metallic roof, like a roof made of metals, it's going to be magnetic, right? So you need to map that. So when you interpret your data, you don't take this magnetic anomaly for geology, you assign that as the infrastructures. And then there is also the regolith. So in Ghana, you get a lot of rain, the rocks you have on surface are not the basement rocks, and what you want to map is the geology in the basement, right? So you need to be sure that geophysics is not showing you physical properties of the regolith. So this is a map of the regolith. So you need a map of the regolith. So if we see any magnetic features along that, we are going to suspect that the geophysics is not showing us the basement, but it's showing us the regolith. And then we can overlook that. So now you can look at your magnetic data. So that's the minus 30 second vertical derivative. Don't worry if you don't know what it is. It's all good. So the strategy is the same as before. You're going to use this thing to map the primary fabrics first. So you try to map rock layers. And rock layers in geophysics, they are going to look like rock layers on the outcrop. So they are going to look like planar features, so elongated anomalies that are all parallel. Sure, that's how layers are going to look like. So here you can see what I mean. But you may see, oh, how did he figure out the rock layer in this zone where everything is flat and we see no contrast, right? Because we don't see much in this area, right? So again, sometimes your geophysicist is going to give you a JPEG, which is going to be that, right? But with this JPEG, you cannot see anything here. It's all gray. But you can see that I was able to map a lot of structures, and this is because I didn't get the JPEG, but I got the raw data. So I can stretch them, and I can start seeing more subtle magnetic bodies. And you can also...
Sorry, Frank, but you do that with the image. You don't work with the data.
Yeah, we work with a grid file. Yeah.
Okay, so you just contrast and stretch.
Exactly. Okay. Exactly. But if you are given a TIFF or a JPEG, you can do that. It's gonna, yeah. And you know another thing you can do, you can contour. I haven't done that yet. Yeah. So what did I do? Yeah. So you can identify folding. I think that was the purpose of this image. I'm going to go super fast. And then intrusive. So intrusive, basically what they're going to do is they are going to cut your layers, but they are not going to offset them. Okay? So that's how you recognize intrusive. So like if you have a layer here, and you have the same layer on the other side, and you have a body that has an ovoid type of shape, a good candidate to explain that would be an intrusion. So that's how you can recognize your intrusion. And then dikes. So dikes, same story. So dikes are unlike intrusions like this one, instead of being ovoid, they are going to be planar, so they are going to be elongated. And when you have a layer coming from one plane, it's going to continue on the other line without any offset, so you know you're looking at the dike. And for faults, it's the same thing, except that for faults you have displacement. So when your layers get cut by the fault, you're not going to find it on the other side. It's going to be displaced. So that's how you organize your faults. And then how do you determine, so the faults have different colors, so different edges. And you can organize the edges using cross-cutting relationships. So here the dike is not offset by the fault. The layers are offset by the fault. So the fault has to be in between the edge of the dike and the edge of the layer. Another way you can figure out the edge is by looking at the orientation of the structures and looking at what we know about the edge of structures having the same type of orientation. And so you can guess the edge many ways. Okay, but you need to have the edge because only the structures that were active during gold time are going to be forming deposits. So I think I'm going to leave it here because so after that you get your interpretation. And yeah, and I'm going to stop here because after that, you know, for retargeting, it would be a similar process as for Cerro Negro. You would need to utilize ArcGIS to figure out where your target would be based on the structural controls you have there. Sorry, it has been super fast, but I hope it gives you an idea. And sorry, I went over time. Sorry, I went too fast, I think. For this one, I lost you along the way.
Bueno, le agradecemos a Franck el tiempo. Yo por ahí le quería agregar un comentario que en clase lo hacemos y lo venía charlando con Frank. ¿Cómo para ustedes, en la generación de ustedes, van a tener que trabajar más con geofísica que con roca, ¿no? Porque los próximos descubrimientos van a estar cubiertos o con pocos afloramientos o van a tener que deducirlos de alguna anomalía o alguna evidencia paleosuperficial y van a tener que deducir que están debajo de eso, ¿no? Los litocaps y todo eso. Entonces la realidad es que hay mucho de esto, un poco por eso yo quería traer esta charla acá y cuando hablamos con Frank, él me comentó lo de Cerro Negro y después me comentó que estaba esta charla y yo empujo mucho a que piensen ustedes que el futuro de ustedes va a ir para herramientas indirectas. Entender la geofísica es clave, porque mapas, como dicen, nosotros trabajamos mucho con geofísica. Rayas podemos poner a cualquier lado, pero después que tengan sentido son muy pocas y están muy limitadas. Entonces, la interpretación geofísica parece fácil, pero es muy difícil. Nosotros estamos todo el tiempo peleándonos con la geofísica y testeando. Lo cual yo de esta charla rescato eso, ¿no? Incluso lo que les decía, cuando un geofísico te da una imagen, a veces no ves lo que vos querés ver. Por eso es importante, y nos pasa a nosotros que trabajamos con los geofísicos. Nos juntamos con los geofísicos y decimos, no, mira, mejorame esto, no me gusta. Porque esa interacción es muy buena, porque el geofísico no es geólogo y vos no sos geofísico. Entonces, saber lo que te da cada herramienta para poder potenciarlo es lo mejor trabajando en equipo. Y bueno, a eso les quería comentar. Bien.
Gracias.
Gracias.
We have a little press.
Oh, that's cool. Muchas gracias. Muchas gracias. Excelente. Actually, yeah, cool because yeah, that's great. That's awesome. Muchas gracias. Yeah, excelente. So, du vin argentin. Muchas gracias. And if you have questions or if you want to contact me, don't hesitate. Diego has my contact. So if you have questions, you can contact me by email and answer you.
Yes.